Okay, we're going to look at a topic called significant figures today. And before we get into the rules for significant figures, we're going to look at two ideas that are really important in science: accuracy and precision. Here I just wrote down the definitions for you. Accuracy is how closely individual measurements compare with the true or accepted value. So how close is my measurement to the actual value? That would be talking about accuracy. Precision is different from accuracy. It is looking at how closely individual measurements compare with each other. So it isn't considering the true value or the actual value. It's looking at, when I repeat measurements, are they close to each other? So here we have some visual representations with targets expressing these ideas of accuracy and precision. And let's look first at the high accuracy, high precision, because some of you might have different ideas of what great precision is. When you're target practicing, this might look really good to me. I would think that was pretty high precision. But let's look at really high precision here. We have very high precision. All of these are very close together. They are also very accurate. Look, they're all right there in the bullseye. So that's high accuracy, high precision. Here would be an example of high precision. Each of those shots, they're very close together. They are not far from one another. But the accuracy is low. They are all up here, and the target was right there, the actual value. Here would be high accuracy, low precision. They're not that close together, but they are getting fairly close to the target. Low accuracy, low precision. They are not accurate. They are not at our target, and they are not close together to each other. So this was just a visual representation of these ideas. So are we accurate or precise? So here are some examples. What is the temperature at which water boils? And let's say we take some measurements in the lab, and we get these measurements, 95.0, 95.1, and 95.3 degrees Celsius. And the true value is 100 degrees Celsius. Well, we're in this range. We're very precise. Our measurements are all very close together, but we're missing the mark. We are not accurate. Now, let's say we look at the temperature at which water freezes, and we measure these measurements, 0.4, 1.2, and negative 1.1 degrees Celsius. Those, and the true value is 0.0 degrees Celsius. Those are accurate. They're all very close to the true value of 0.0. And I just wrote this: it is hard to be accurate without also being precise. How about this measurement? Let's say we look at measuring the atmospheric pressure at sea level, and we come up with 10.01, 0.25, and 234.5 atmospheres. Wow, those are not precise at all. They're all very far apart from one another. If the true value is 1.00 atmospheres, we are also not accurate. None of these measurements are not close to the true value, so we are not accurate and not precise. How about the mass of 1 liter of water? And we measure that as 1.000 kilograms, 0.999 kilograms, and 1.002 kilograms, where the true value is 1.000 kilograms. Wow, these are all very precise, very close together, and they are all very accurate as well, and very close to the true value. So those are accurate and precise. So when deciding on accuracy, precision, both or neither, we're talking about quantitative data, numerical, not qualitative or descriptive. So here are just some examples. Look at these examples. See if you can describe them as being accurate, precise, both, neither, what you can determine from these, and we'll look at those on the next frame. So here, if the recipe calls for 25 chocolate chip cookies, or chocolate chips per cookie, and you analyze some cookies and find these numbers of chocolate chips, well, this is precise, but not accurate. Here, if we're looking at the percent sodium chloride, and we come up with these 3 numbers, that's very precise. we do not have a reference to the actual or true value, so we cannot determine whether it's accurate or not. And what about the number of grams of potassium fluoride required? It's 0.04 grams. And we used 0.038 and all of these right here. That is both precise and accurate. And here, to win, Henry must earn 500 points. These are the points he earned. These are neither precise nor accurate. So remember, significant figures are really important. We're going to just do a quick review. Every measurement has some degree of uncertainty. We talked about that in the previous section. Significant figures are the digits in a measurement that are reliable or precise. The greater the number of significant figures, the more precise that measurement is. A more precise instrument will give more significant figures in its measurements. So let's look at some uncertainty examples. Let's say we're going to measure time for a pencil to fall to the floor, for example. Let's look at the difference between a stopwatch and a wall clock. Which one will be more precise? The stopwatch is more precise than the wall clock. The wall clock can measure seconds. We can measure fractions of seconds here to multiple places beyond the decimal. What if we're looking at measuring the volume of a liquid and we're looking at a graduated cylinder versus a beaker? Which one is more precise? So a graduated cylinder is more precise than the beaker. We have 3 significant figures here for our graduated cylinder. We're more precise, the 4, and the 0. Our 100 milliliter beaker, we can only say 40 milliliters. That's as precise as we can be. That only has 2 significant figures. And we're going to talk momentarily now about how do you determine the number of significant figures that you're looking at here. Right here, this decimal point indicates that we only have 2 significant figures, and let's talk about how we know that. So when are digits significant? Rules for counting significant figures are as follows. We're going to talk about 3 rules. 1, non-zero integers. They always count as significant figures. So here's an example. Let's say we have this number. It has 4 non-zero integers, and all of them count as significant figures. So if you were asked how many significant figures is in 1,457, 4 significant figures. They are all non-zero integers, and each one counts as a significant figure. Now let's look at zeros. Zeros, that is the place where we really need to think about a few different situations. We have what's called leading zeros. Zeros in front of the number, okay? They never count as significant figures. Here's an example. We have 2 zeros that are leading zeros. They do not count. But the 2 and the 5 count. They are non-zero integers. So 0.025 has 2 significant figures. Now let's look at captive zeros. They are zeros in between non-zero integers. They always count as significant figures. Here's an example. 1.008 has 4 significant figures because those 2 captive zeros count as a significant figure each. What about trailing zeros? Trailing zeros are significant only if the number is written with a decimal point. So here's an example. This number is not written with a decimal point, so those zeros are not significant. 100 has 1 significant figure. But look, this number is written with a decimal point, 2.0. Therefore, the trailing zeros will be counted. 2.0 has 2 significant figures. Now, one other situation would be exact numbers. For example, I have 3 apples or 5 experiments. Exact numbers have an unlimited number of significant figures. So let's do a little practice. How many significant figures are there? Here are some examples. You try and do some of these, and we'll look at the answers on the next page. So let's look at the answers. 789 has 3 significant figures. These are all non-zero integers as well. We have 5 significant figures. Remember, these zeros are leading zeros. They do not count, so we only have 3 significant figures here. These are all non-zero integers, 4 significant figures. This is a leading zero, so we only have 2 significant figures. Here, I wrote a number in scientific notation for you, and in this case, we just look at the digits right here. We have 1, 2, 3 significant figures. They're all non-zero digits. And here, we have trailing zeros and a decimal point. So we will count those zeros because they are trailing after the decimal point. That gives us 4 significant figures. Now we have one more idea to talk about here, significant figures in calculations. So now that we know how to count how many significant figures are in a number, we will need to figure out how many significant figures then can be in our answer when we make calculations. And it's important, here's the big rule of significant figures, your calculation is only as accurate as your least accurate measurement. So if I take a measurement and I have 3 significant figures in it, and I take another measurement and I have only 1 significant figure in it, I can only be as accurate as in my answer, if I'm going to do some calculations with those numbers, as my very least accurate measurement. So let's do some specific examples, and we're going to first look at multiplication and division. When I multiply and divide, I will round my answer to the number of significant figures as the data point with the fewest number of significant figures. So say I have mass and volume, and I'm going to tell the density of something, of some substance. Well, that's going to be 212.3 divided by 36. That's going to give me this number on my calculator, right, in grams per milliliter, great big long number. I don't want to write all of those sig figs down because I am not that accurate. I am only as accurate as the least accurate of my measurements, which is 36. It has 2 significant figures. My mass has 4, but I can only be as accurate in my answer as my least accurate measurement. Therefore, my answer will have to be rounded to 2 significant figures. Now remember the rules of rounding. We look at the 5.8, and then we have to look at the very next number, 9. If the very next number is a 5 or greater, then we will round up. Well, 9 is 5 or greater, so we're going to round up, and our answer will be 5.9. If that number after was 4 or less, a 4, 3, 2, 1, or 0, we would simply leave it as 5.8. But our answer is 5.9 grams per milliliter. Now let's look at addition and subtraction. When we add and subtract numbers, we will round the answer to the same number of decimal places as the data point with the fewest number of decimal places. So let's look at an example so that makes sense. Let's say Billy, Sally, and Ed all contribute some amount of money. How much money do they have? When we add these numbers together, we get $5.70 as an answer. But we need to look back here at the number of decimal places and the data point with the fewest number of decimal places. That would be the 5. It has the fewest number of decimal places. So it has none. So we are going to have to round our answer to just the ones place. Now remember the 7, it is 5 or greater, therefore we will round our ones place up to a 6, and we can only be as accurate as $6, and that's it for this answer. Advanced proficiency. How would your calculations differ if you use significant figures throughout versus if you chose to ignore them? It's always an interesting way of looking at significant figures. For our purposes, we will be maintaining all of the digits through the calculations, and then you will round your final answer. So that is how we will proceed. However, if you would like to do a little exercise and just prove to yourself how different answers and calculations can be, depending on if you use significant figures throughout or if you would round them at the end, there oftentimes can be a significant difference. So can you think of a real-world example of when this would be important and why you think you might need to be really careful with your numbers, with your calculations, and with how accurate you think you are being? So I look forward to seeing you in class.